It's synced.
Yeah, I see it now.
Nice. So we are starting a chapter called Partial Derivatives, and the first 1.1 is function of several variables. Finally, we will teach you what I mentioned what is 1 and 2. What happens when you have a function that depends on many variables? X, Y, Z, G is the gravity, T is the time, I don't know, the consistency of the airflow, or the temperature of the room, or how many times you coughed during the exam on Wednesday. That was very scary. And so on. So like many variables in one function. What do you do in that case? You should understand an extra variable adds a dimension. So if you want to consider all those things, and you should when you're modeling, that increases dimensions, and that is hard to work with upper dimensions. So your function, the function of the several variables, in this case let's do 2, is a rule that assigns to each ordered pair a real number. In a set D, a unique real number denoted by f of x and y, or z. Basically the same thing. We used to have input x, output y, or f of x. Now we have input x and y, output z. So basically the machine, which we usually show you, the function is the machine that takes something in and spits something out. Now it takes in a couple x, y, and it spits out z. So it does something with a couple and give you out z. Now you can imagine you can have thousands of variables in and then 3 out and so on. So the domain now is a set D, not just one variable x. And the range, did you see this notation before? Braces. Braces means a set. Z equals f of x comma y. Bar means where or when. Where x comma y is in D, where D is domain. Basically it says this is my input and this is my output and my rule. So equal sign means a rule. X squared minus sine y plus some logarithm. So this, did you see the notation of braces before? We try to teach in the calculus classes. Braces means a set of z equals f of x and y, where x and y belongs to domain D. X and y now are independent variables, not just x as we used to have. And z is a dependent variable. The graph of f is the set of all points x, y, z, 3 dimensions. In R3, usually people put R with the bar. Oh no, actually I'm wrong. That is real numbers. There are 2 ways to show it. Some people do real numbers cubed, like so. Some people do just R cubed. Actually, I'm right. Depends on the book. Such that z equals f of xy and x of y is in a domain D. That is actually the same thing, they just repeated. The graph. So for now, it's not really new. Instead of f of x equals y, now we have a third variable, z equals f of xy. Not yet. Let me know. Hey, you have the notes. I gave you the link. Don't distract people who sit behind you. It's very easy to kick your ass from there. I should not say it when I'm recording. The domain of 2 variables. So this is how it looks like. Look, it goes through the shadow. How cool is that? So I told you before, some awkward shapes, which we don't call surfaces, in 3D have shadows. Now this shadow, which we now know, this word projection, is called a domain. So check this out. I give a function, I feed into the function concrete x, which is here, y, which is here. This is my domain. It's restricted only in this whatever shape it is. And then the output goes up as a rocket and shoots and fixes this point upstairs over here. Next point, give me next point, and that's how you create a surface. A surface might have some odd or interesting shape, but domain is a shadow. Projection, yes.
How are we going to see range in this sort of graph?
We will do it right now. You'll see.
No question. How about that?
Spoiler person. So, input is x comma y, and then output is f of x comma y, which we also call z. So that is a three-dimensional two variable function definition. So this range is all this shape, domain is in 2D. Now, examples of two variables, x and y. I give you x0, y0, and z0, but what if it's x, y, and z? 2x, you don't have to write it down, it's just fun examples. And then and so on. The more you put, the more fun it gets. So when I was modeling epidemic spreads, we have lots of variables. Sometimes they represent patients, and there's many patients. Sometimes they represent the speed of the vaccine working, immunity, the speed of transmission, and then recovery, and all of this. If you do project with me, that's what we're gonna do. And all of this is in one function. So as many functions as you want can be there. Examples. Let's learn something to proceed with your homework, which is, by the way, due Monday. Just for you to know. If it's too hard, I might consider postponing to Tuesday, but I want to do quiz on Wednesday, so you need to finish before Wednesday. So if so write this down. If f of x comma y, and get used to the notation. Why on the exam people gave me a point like this? This is so wrong. Why? A point should be like this. So I took points off, but I don't know how many to take off. How many do you think I should take off?
0.1.
For now, I actually took half a point.
Oh.
But like, point is parentheses, vector, not parentheses, and I even gave you x comma y equals, and then you gave me this, like what?
It also could be read. It could also be read differently too, because I think they could have meant the parentheses.
No, but I put I wrote the parentheses. So upsetting.
That's a vector. No?
Anyway,
Wrong answer. 0.
2x squared plus 3xy plus y squared. Find f of 1 and 2, and the other one I don't want 2, just 1. Let's do 1. So solution. How would you do it? What is f at 1 and 2? Guess what? Everywhere, take a pencil, specifically for your first homeworks to make sure your brain gets used to it. Because brain got used to, for 10 years, you're learning math, got used to x and y only, input, output. Now your brain have to requalify itself to have a third variable. So at first, it's convenient to make this visualization, especially if you are a visual learner. X is 1 and y is 2. So everywhere you see x, it will be 1 squared plus 3 times 1 times y, which is 2, plus 2 squared, right? So, and so on. You can do that. That is not a big deal. What's the answer? Who knows? 12? I will just believe whoever said 12. So, applications, so many applications, you don't have to write this down. But multivariable functions are useful in real life since life itself depends on so many variables, like I mentioned in epidemiology and engineering. For example, f of t and p, its temperature and pressure, r and p, position and momentum, that is quantum mechanics. Finally, x to the alpha, y to the 1 minus alpha is in statistics and economics, I remember that, probability theorems, and so on. Let's learn how to build domain and range, like you asked. Functions in several variables have graphs. The only difference is that in one dimension, graphs are curves, but in 2 dimensions, graphs are surfaces. Curves are lines or parabola, hyperbola, whatever we had before. Surfaces are things like sheets and like this ghost we just saw. So we will see examples. The definition is a domain of a function now is a set of numbers x comma y, or z and t and m and g, how many you have, for which f of those variables is defined. Nothing new. Basically, domain is where your inputs, where the outputs are defined. Domain are allowed inputs. You cannot have inputs outside of the domain. Sometimes it doesn't even make sense, like plugging negative numbers into the number of patients. So number of patients should have domain positive, right? And so on. range of a function is the output. So a function f is a set of all possible values of z, so output. What is my output after I check out the domain? So that my, I would say, possible or allowed inputs, and those are outputs. Same thing, there's not anything new here. But now the hard part of the homework starts now, when you actually have to do your work by yourself. So let's do it. What is happening with a function f of x comma y equals square root of 9 minus x squared minus y squared? Let's work on that. Yes.
Oh, I didn't know the
Oh. No, let's do it step by step right now. It will be more interesting for people. But good job. It's nice if students have nice visual qualities. It's good if you have good imagination in this class. That will help you. But if you don't feel bad about it. It's fine. But it's helpful if you can visualize everything. So, we've seen this object before. Let's rewrite it. Solution. Z equals a square root 9 minus x squared minus y squared. Like so. Now, okay, so this is a definition. I just basically called this z. I did not do anything yet. Now let's do something about it. Let's square both sides, but remembering that the square root actually restricts the domain. We will do it later. Z squared is 9 minus x squared minus y squared. Maybe let's rewrite it to kick out the constant. If I move these guys to the left, I will have x squared plus y squared plus z squared equals 9. Does this remind you something?
Circle? Sphere.
Not a circle, a sphere. Yeah, good job.
Radius 3.
Yeah, exactly, a sphere. And also there will be a difference between a sphere and a ball. A ball is filled in inside. So that will be different. A sphere is only the outside. So a soccer ball, a football, okay?
Yeah.
A real football, not the American football.
Yeah, there's only one football. You actually kick it with your foot.
I know, right? Football.
I did that, man. I did both.
So, you believe it is a sphere. Do you all agree on this?
Well, now I'm doubting myself.
No, you don't. Yes.
When you squared the z, you also didn't. We said that it still restricts the domain.
This.
So probably not.
This is important. He is right. This is important, right? Let's not put exclamation mark or it becomes factorial. Z is only positive for 0, so it's already not a sphere. Sphere goes up and down. So before squaring, you always have to make a note. Don't forget, before you squared, it was important. So since z can be positive or 0 only, then the graph is actually, how would you call it? Semisphere, amazing. Or we also call it upper hemisphere. Hemisphere is a synonym of semisphere. Semisphere. Upper, so we also know where it is. If it's less or equal than 0, then it's a lower hemisphere. Centered where? Centered, thank you, 0, 0, 0. What's the radius? 3. Because it's 9, so 3 squared. Agree? So that's how you plot things in 3D. This is 2 variables. Every input into D, which is on the floor, will be shooting up with the next rule, 9 minus x squared minus y squared, and then you take the square root. With this rule, slowly it builds up all the surface. So now, instead of curves, we have surfaces. The surface is completed, and it appears to be the upper hemisphere. That's the idea of multivariable calculus, that there are now 2 inputs in a domain. But also see, in 3D, so we did not work in 3D before we took this class, right? Never we had it before. We were working on the floor. We were like ants walking on the floor only. We did not know that there's 3D things. So for ants, this is a circle, right? Very interesting. Now we kind of opening the window into multi-variable function world, and we see that actually it's much bigger than that. It can be different shapes. Yeah.
Obviously, this is like a very easy example to explain, but if we move this circle up 4 points, sorry, this upper hemisphere up 4 points, then it would be a full sphere.
Oh.
It is translated up 4 points on the wall.
Very interesting point. So z is still restricted from 0 to plus infinity, but if you move it up,
if we
yeah,
translate it
yeah,
up 4
good point. Yeah, it will like go out like a whole sphere from the ocean. Yeah, yeah.
So how do we?
You will see examples like this actually. Yeah. I see. I actually don't need you today. Why did you come?
Next class.
Oh, for the next class.
Yeah.
I see. Okay.
I was needed today.
You can take a seat. I just want to make sure. Yeah.
How are we gonna see that? Because like, if for example, this was like square root of 9 minus x squared minus and then parentheses.
Oh, vertical shift. Remember we had the vertical shift, so plus 10 like so means going up, plus 10, that might fix it, and so on. Yeah, good point. I wanted to mention I had a TA very like 3 years ago. I think it was my first TA ever. And then I was teaching the class and I needed her help. She came and then she came and then we finished the work with quiz. And then instead of sitting and grading, I used to give quizzes at the beginning of the class. She was standing like so and like looking at the class. And I started teaching. And then it was really awkward. I started turning around like, why do you keep standing? And then she says that in her other classes, teachers forces her to stand still all 45 minutes. And like, for some reason, I don't know. And that really bothered me because that's also very annoying. Like, why is someone standing behind me? And I'm like, you can go. First of all, take a seat and rest. Second of all, you can start grading. She's like, can I? Like, yeah, you can. Okay. And since then, my class was the only class she could actually sit down. In all other classes, she was standing. That was so weird.
Was this my Calc 2 class?
No, it was some kind of pre-calculus, I think.
Oh, okay.
It was not you also.
Okay.
So, in one-dimensional domain is an interval from 0 to infinity, but in two-dimensional domain is a 2D region. Here, the range is in fact an interval, like 1. So, let me show you that. Let's explain this a little bit more. But domain and the range. So what is the range for this function? Let's call it here. Range. What do you think is the possible outputs for z? Z belongs. What do you think? Where are my z's here? 0 to 3. So z is not a sphere or hemisphere, okay? Z is still a third coordinate, upper, that looks up. So z is this thing in the red over here, is the interval, and this is my domain. Just like in calculus before, not domain, sorry, that's range. Just like in calculus before, range is it's a range, literally in English, it's a range of possible outputs. So we including 0 and including 3. Which interesting that it is in the interval, but it's not always an interval. In this case, range is 2-dimensional, it's an interval. Very interesting. Now, the domain here, let's see. But domain used to be an interval before, but now it's a 2D region. So let's write down what is a domain. Domain is my projection on the plane, which now we know how to call it, xy plane. Domain is now has 2 variables, x and y. And this is a circle. Circle. So y, circle. What kind of circle? Centered. Centered at 0, 0, 2 dimensions, right? And radius, let's call it small radius, 3. Does it make sense? So domain is your shadow on the floor. Domain. Range is how far my z goes. So that is interesting. And that's going to be a challenging part for you to see different 3D regions. So when you see someone else is doing it, it's straightforward, but when you're asked to do it yourself, this is where you're going to be a little bit challenged, which is fine. Limits. Look how cute this limit looks like. X comma y goes to 1 comma 2. Now imagine like 5 dimensions. X, y, z, t, m goes to 1, 2, 0.5, negative pi, and so on and so on. Then you have different functions here. Same thing, your brain just needs to requalify how you see things. This is x, this is y. So x goes to 1, y goes to 2. X goes to 1, y goes to 2. The answer is 2 times 1 is 2, 4 times 2 is 8, 1 squared is 1, 2 squared is 4. So it's 10 over 5, which is 2. Makes sense? So the interpretation of this, do I have it here? Yes. The interpretation of limits used to be when x approaches something, y approaches something. In this case, it's a little bit different. When x and y both approaching something, f of x comma y approaches something else. Or the same thing, doesn't matter. So interesting, 2 inputs, 1 output for limits. So that's approaching, limiting position. Yes?
Where is it approaching from? 0, 0?
It's in 3. That's a good question. Let's see. If you graph, again, imagine it's a surface, so whatever it looks. I can draw it right now in Wolfram Alpha and C. When x and y, remember that there is these guys here. X is 1, y is 2. So it's something here. When x approaches this direction and y approaches this direction, so they both go to this point, f of x from the left, from the right, from the front, from the back, from all the directions, approaching this point. So it's a very good question, how does it approach? And soon we will have to figure out what it means. So something like that. Very good. And this is z, as you understand. Z is 2. That's a very good question. Now, if we define limits, we can define continuity. Intuitionally, it's the same thing. No gaps, no jumps. Means the function is continuous. But this graph looks pretty cool. You don't have to write down the definition below. But if you took classes with someone else, but not me, maybe you were lucky to see extra delta definition of the limit or continuity. I usually skip it, but in pure math classes, we always define everything with epsilon delta intervals. But anyways, the idea is pretty cool. Domain, here is your x and y, that's my input, shoots up to the surface. Surface, this domain, say it's a circle, maps on the surface, but surface is not flat, it's curved. So what is a circle on the curve? It will be some kind of jammed circle. So it's very interesting, the domain is still a neighborhood. Remember, the domain idea is a neighborhood. I am in a domain of this circle, means I'm around this point, A and B. Being around the point on the surface means climbing, hiking, going up and down, and so on. That is a very interesting problem, which you might heard about, how to map our world, the planet, right? The planet is a sphere. How to create a map, and that's why it's not realistic. I think I mentioned calculus too. Australia have a weird size than there, and Canada also, and so on. So, because, for example, if this is your country, looks like a perfect triangle. What is a perfect triangle on a sphere? Isn't it like something weird like so? So that's why mapping is a whole science. How to carefully map 2D into 3D, domain into range, into multivariable calculus. And that's what we're going to try to teach you. Some sneak peek. Level curves. Today's class is actually about level curves. So Level curves, this is all your homework is about this. Let's take a look to the next level of 3D and see what level curves are. This is a useful tool for graphing functions in 3D, 4D, 5D, and so on. Consider the function f of x and y and see the graph on the left, some kind of bell, right? Now, we can take a look what is happening at level 5. So again, this is z equals 5, z equals 10, z equals 15. When I'm fixing the level, and that's what it's called level curve, when I'm fixing the level, the height, now I'm ending up to be 2d. Why? Because z is 5. That is a fixed constant. Now, when z is fixed, that is not a three-dimensional object anymore. It's a slice. Imagine your ninja throwing the knives into this. It's slicing through, and the slice gives you a circle, red circle, looking like so. Z equals 5. If I'm slicing at level 10, as you can see, it shrinks. The circle becomes smaller. If I'm slicing at level 15, it becomes a point. So you're slicing a nice looking cake. The biggest circle is at the bottom, 0 level. 0 level gives you the biggest circle. That's what we call contour mapping. So these are called level curves. This is what you see in 2D as the bug, the ant, sees this notation. Also, they usually color coded. The bug doesn't understand what it means until it starts climbing to this. And apparently the height will be like so. Bottom to top, 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 top. And this is the peak of the mountain. Have you seen the contour maps before? What does it remind you?
Topographical maps.
Topographical maps. I will show you here first. This is why they are created, right? Topographical maps is the human being idea to show heights on the flat surface. 3D onto 2D, usually using colors and representation. But the idea is if they're close to each other, that means one thing. If they're far from each other, means something else, and so on. So we need to learn these things. And I've created lots of cool animations about this. Not created, found. Here it is. See? Level curves and the domain. You see, the domain is still a circle, but the shape is different this time. So the moment I fix somewhere, 2, 3, 4, it gives me different shape at the bottom. That means level curves give me different slices. Increasing, then it stops, but then it will shrink again. Level curves. Idea is straightforward, but working with them is a bit challenging. Now, so don't have to write down this yet. We can look at all the points that are given height. For example, all the points that are height 10 and all the points height 15, the curves that we get are called level curves, and the picture that we get is called a contour map. Definition: level curves of the function are the curves with the given equation f of x comma y equals k. K is a number. So this is kind of the definition. Z equals, I'll write down, k. Some kind of number. When you fix the height, means you give it a number. It's like, oh, we lost a hiker. We got from the radio, the hiker mentioned that he's an elevation of 1,000 feet. This is fixing the height. 1,000 feet were fixed. Now the helicopter just need to go around the mountain of that height and find the hiker. Make sense? So that's the idea. Now, this is projected on the XY plane like a shadow, and the graph of that projection is called contour mapping or a plot. Here it is. The thing is, it can be different from whatever you fix. At this point, it will be a dot. At this point, it will be a perfect circle. At this point, it's not even a circle anymore. Apparently, its shape shifts. And that's why it's also very interesting that it can be different. Think of the level curves as slicing the graph horizontally and the contour maps like a bird's eye view of the graph. These are pretty cool. You don't have to draw this. I will give you those maps. But it is pretty cool. This is not the same. This one, look at this. On the floor on 2D, This is what we see in topography, right? This represents it goes up, and indeed it goes up in the middle. This also represents that some kind of peak is happening, but it's going down. We need to learn how to distinguish this. These gaps means valleys. These circles, and when they close to each other, means hiking or gradient is going up and down. Today, I was told that you maybe start gradients already in your physics class. So we're gonna go there next week. This is what we see in 2D. So valley, hiking up. The more curves you see, the harder the hike is. That's all. So below are the used maps to draw into the representation of the mountains. We got this. This is also a pretty cool idea. It's usually they are color coded. The brighter colors indicating the top, the darker colors indicating the bottom. And that's also more convenient when people figure out how to color, and especially coding and computers show up. That makes that science more interesting. So what is this shape? Look at it, if it's color-coded. Now, what I told you, what do you think it is in 3D? So you are an ant looking at this in 2D, but now you're a bird and you can see this in 3D. What do you think this is in 3D? 4 mountains. Well, 2 mountains and 2
Valleys.
Is it valley or like deep depths?
Yeah, that's a valley.
A hole.
I thought valley is a flat.
No, valley is like a concave down. Like
Oh, so what is flat then?
Flat is just plain. Plateau.
Oh, plateau. That's the word.
Plateau is up here though, isn't it?
Yeah, plateau is so just be a
Yeah, plateau is where you climb up and then you cut right here. Plane is where it's just like
plane just flat. If it's just all light green, then that'll be a plane.
Yeah, that's
Right. Red ones go up. You want to go down. So if you remember correctly, this
Well, if that's
That's a hole. Yeah, that's a hole.
2 mountains and 2 valleys, right? Pretty cool, right?
I think that's more of a hole than a valley.
Pretty cool. And we will learn soon how to find this point. This is the point. We will have to learn how to identify. We will have, now you can have a visual where this mass is going. Absolute maximum, absolute minimum, local maximum, local minimum. What is this point? We're going to learn this next time. Optimization problems. Oh yes. Oh yes. Now. Oh. Why?
That's a good. Yeah. That.
Okay.
Oh, there it is.
Something worked. Those are also different level curves going around. Let me see if I have them here. We saw this one. Yes. This one. This is there. Well, check the Wikipedia page. It has very nice stuff there.
Oh.
We're gonna go there right now. Okay, then actually it's fine. So, sketch the level curves. Ton. And this is what your homework is about. Oh, look at that. They don't work. I wonder why.
I think any of those things are like Google user content. It's like they only work in the moment that you're actually getting the link.
Oh, I see. Interesting. So sketch the level curves for y equals, we had this function before, but now we are asked, let's figure out what's happening at 0, 1, 2, and 3. How do you do that? You literally plug it into equation and solve for it. So let's do that. How you are going to do it? Lots of algebra. So this is my question. What is going to be in 2D? We just draw this picture, but we don't know how it looks in 2D. So let's write it down. Z equals 0. Z equals 1. Z equals 2 and 3. What do? You look at the equation. Oops. And you literally write it down. It will be 0 equals a square root 9 minus x squared minus y squared. And you need to solve it to see if you recognize this shape. Well, let's square both. That is going to be 0 equals 9 minus x squared minus y squared, right? Okay, maybe rearrange. That is going to be x squared plus y squared equals 9. Do we recognize this shape? It's a circle. And that's what you would expect from over there. And now you draw it, right? In 2D, let me have it here. in 2D, you draw a circle, maybe in different color, center at 0, radius 3, and don't forget to match, to remind yourself, radius is 3, you will forget. Now, 1 is more complicated because now you have to solve this for 1. It's fine, square both. 1 equals 9 minus x squared minus y squared. Now, x squared plus y squared equals what? 8. So circle is shrinking,
Makes sense.
right? So now I have, so I guess that should be, that was supposed to be the biggest one. Let's do like so. R equals 3. Now, what is this radius? Square root of 8. R equals square root of 8. Now, and you keep going as you understand it's the same thing. 2 equals the square root. 4 equals 9 minus x squared minus y squared. X squared plus y squared equals what? 5. So, that was blue. This will be pink. So it seems like the radius is shrinking, and that's exactly what you would expect in different levels. The level is going up, right? Level 0, level 1, level 2, and then you can see that the circles are shrinking. I do actually have the answer. Ta-da! I was hiding it from you. How smart is that?
How fancy.
I know. I did it today in the morning while drinking coffee. And so on. So the level curves are 0, 1, 2, 3. Those are heights, right? And they all center on 0. And then radii, you know, radius is radii, right? Is 3 squared of 8 squared of 5, respectively. So it's great about what's great. Let's see. Do you have questions about this? Yeah. What is great about the level curves is that they can give us a 2D representation of a 3D picture. So sometimes we don't know 3D picture, we do know 2D picture. And then you can kind of create, just like in 2-dimensional with data science, sometimes you know the dots. And then just like in kindergarten, we know how to connect dots. And you're like, oh, I know the shape. It's a curve. Same with level curves. What if you do know level curves in 2D? And that will give you some kind of imagination of what is 3D picture looking like. For example, use level curves to find the unknown surface, x squared plus y squared equals z squared. So now you can plug all kind of random points, whatever you choose. For example, let's check level 3, let's check level 2, let's check level 1, let's check level 0. How do you do that? You keep plugging in. You have x squared plus y squared equals 3 squared. You have x squared plus y squared equals 2 squared, and so on. But wait, why keep choosing positive? Let's choose something negative. Minus 2 and minus 3 and 0, right? X squared, no, it should be fine, don't worry. It should be 0, x squared plus y squared, but minus 3 squared is still 9, right? And so on. So what are these? These are still circles, but they just go up and down. So when I draw these circles, I'll move back just in a second. When I draw them, I get the left-hand side picture. So I'm going down from the other direction of the signs. I know the level curves, and I can see they are increasing when I increase z to plus infinity, and they are increasing when I increase z to minus infinity. And then in 3D, they look like this. I do know the height of each. Z equals 0, 0 height. Z equals 1, 1 height, minus 1 height. 2 height, minus 2 height. Now your imagination can kind of tell you the shape of this 3D object. That is a cone. Right? That is called a cone. I know. How cool is that? Do I need to go back? Did you write it down something? So, I will scroll a little bit faster right now, but there are some important shapes you need to recognize. We don't require you to memorize them, but kind of it would be nice if you're intelligent enough to recognize spheres. X squared plus y squared plus z squared equals r squared. That is a sphere. So it will be a lot of drawing if you start doing it right now. I would recommend to have those notes and just copy them because there are lots of them. Ellipsoid is a sphere, but the 3 radii are not the same. Different radius to the right, different radius down, different radius up. X was changed, Y was changed, and Z was changed by different values. Ellipsoid, which is ellipse in 3D. Paraboloid, which is shapes are made from parabolas. These will be very important in this class. We will see them quite a lot. Paraboloids, and I found some applications in real life for you if you want to know. Z equals x squared plus y squared. You see, Z have no squares. So it's just lots of parabolas at every level. Now, types of paraboloids. Z equals x squared plus y squared, or just x squared, or x squared minus y squared. So this is a typical one. We're gonna be using this one quite a lot, which looks like what? What did you say? Both answers are good. Pringles and a horse. What did you say? Saddle, yeah. It's called a saddle, hyperbolic paraboloid. It's still paraboloid because it's made out of parabolas. Here they are. Parabola, 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 So you're sitting on a parabola when you're riding a horse, right? But it also is your favorite chips. So we call it saddle. We will have to work with saddle points quite a lot because it's pretty important part of science. So they both have hyperbolas and parabolas. Hyperbolas are over here, like so. And so on. You can take it, you can get it after the class. Here are the Here are the applications I found for you. And even gave you the link to check it out. Look at this shape. So civil engineers, you guys will be building this, you know. All these structures in Japan and Mexico and so on. Cones, we just built one cone. Cones, think of the circles that are getting bigger in both directions, up and down. We just figure it out. Now, sometimes, I never heard the dress definition. Dress, I do remember hyperboloid. That's the one I learned. Of one sheet. Basically, it says 1 minus makes a hyperboloid of one sheet. It looks like a dress or nuclear reactor. I like how it jumped from the dress to like nuclear reactor really fast. It is important that 1 is above, so it's 1, not any other number. 2 cups. This is important. Hyperboloid of 2 sheets. A cylinder, we will be working with cylindrical coordinates quite a lot. So equals 1, not z, means technically speaking height is fixed and you go up and down and so on. Whatever is a variable is missing, that is a cylinder in that direction. So if x is missing, it will be lying down cylinder. Okay, level curves of, and this is what I wanted to show you is 5 dimensions, okay, because this is pretty cool, okay. Hypercones, look at that. W or omega, let's go with omega, equals f of x comma y comma z and it's square root of x squared plus y squared plus z squared. This is called hypercone.
That's a cool.
Yes, of course you'll see pictures. How cool is that? So again, this level surface in upper dimensions is still the same. Whatever your output, fix this output and that will give you a level curve, right? In this case, it's the output of 4 dimensions, or 5 dimensions, that's 12 dimensions. So hypercones, if I actually trying to fix them, I do exactly the same thing. I'm fixing the height, solving the equation, and then trying to remember what this equation means. And that's why I just showed you those typical equations of the cone, spheres and cylinders. That was the question? No. And this gives you this interesting shape. So level surface gives level surfaces as spheres centered at 0, 0 with different radii. So at any fixed location, there's a sphere. How would you mention the collection of spheres on top of these spheres inside of the sphere? And that is why we don't plot 4 or 5 dimensions, but we can imagine how they look like. For example, in this case, we have 2 cups, a cone, and a dress at the same time, and that is our projection in 3D of the same shape from 4D. So again, there's a 4-dimensional object, and we as a human beings, we're dumb down, we cannot imagine it, right?
Yep.
So there's like a 4-dimension, and it's only 4 dimensions, not even 5 or 10 or 100. 4 dimensions, there's a shape floating there. We as ants only see a shadow of the shape into Z plane, X plane, and Y plane. And on each shadow gives you already 3-dimensional object, a sphere, a cone, or whatever, dress. And then you're like, wow, so what is this object even mean? And that is why it's so hard to represent it. And I did find you this animation, which is exactly what is a hypersphere. This, the one I showed you at the very beginning. If you start slicing a watermelon, what it gives you are smaller watermelons. How cool is this?
Professor?
The watermelon is in 3D, and it's the projection from 4D. So if you start slicing it, every moment it gives you a sphere. So watermelon creates a watermelon. How cool is that?
It sounds like a Russian doll watermelon thing.
The
Russian doll watermelon.
Russian doll. A 4D Russian doll.
Monday will be amazing. So 2 days off.
Thank you, President.
You're welcome. You see this?
Jacob.
Jacob.
Wait, 2 days off?